Hello, I am Dr. Srinivasa, working as an assistant professor of physics. In this video, I am going to explain some concepts of polarization for 2nd BSc 3rd sem students. In this session, I am going to explain what is retarding plate, types of retarding plates, what is quarter wave plate and how it works, what is off wave plate and how it works, and what is off wave plate and how it works. What is a retarding plate? A doubly refracting plate cut such that the optic axis is parallel to the refracting surface and the thickness of the plate is such that it produces certain phase difference between the ordinary ray and extraordinary ray is called retarding plate. A doubly refracting plate cut such that the optic axis is parallel to the refracting surface and the thickness of the plate is such that it produces a certain phase difference or a path difference between the ordinary ray and extraordinary ray is called retarding plate. There are two types of retarding plates. One is quarter wave plate and the second one is off wave plate. What is a quarter wave plate? It is a crystal plate of doubly refracting material of uniaxial crystal cut with its optic axis parallel to the refracting faces and whose thickness is such that it can produce a phase difference of pi by 2 or a path difference of lambda by 4 between the ordinary ray and the extraordinary ray when monochromatic plane polarized light of wavelength lambda is incident normal to the surface. Quarter wave plate is a doubly refracting material of uniaxial crystal cut with its optic axis parallel to the refracting faces and whose thickness is such that it can produce a phase difference of pi by 2 or a path difference of lambda by 4 between the ordinary ray and extraordinary ray when monochromatic plane polarized light of wavelength lambda is incident normal to the surface. Why it is called quarter wave plate? Because it can produce a path difference of 1 by 4th of wavelength, that is quarter the wavelength between the ordinary and extraordinary ray. That is why it is called quarter wave plate. As light is incident normal to the optic axis, the ordinary ray and extraordinary ray components travel in the same direction but with different velocities. We can obtain the thickness of the quarter wave plate. In calcite, the negative crystal. So, calcite is an example for negative crystal. Velocity of the extraordinary ray is greater than the velocity of ordinary ray. Hence, refractive index of the extraordinary ray is less than the refractive index of ordinary ray because refractive index is equal to ratio of the velocity of light in air or vacuum to the velocity of light in medium. But for a negative crystal and for extraordinary ray, refractive index mu e is equal to C by VE maximum because velocity of the extraordinary ray is maximum in a direction perpendicular to the optic axis. As VE is maximum, refractive index is less. Hence, refractive index of the extraordinary ray is less than the refractive index of the ordinary ray for the negative crystal. If D is the thickness of the crystal plate, then the path difference between ordinary ray and extraordinary ray is given by path difference delta is equal to D into mu O minus mu E. Here mu E is less than mu O or mu O is greater than mu E. Therefore, we are taken mu O minus mu E as difference in refractive indices into the thickness gives the path difference for a negative crystal. So the quarter wave plate produce a path difference of delta is equal to lambda by 4. So quarter wave plate produce a part difference delta is equal to lambda by 4, that is quarter the wavelength. Then from these two equations, delta is equal to d into mu o minus mu e and delta is equal to lambda by 4, we can get d into mu o minus mu e is equal to lambda by 4, or equate for the thickness d. So d is equal to lambda by 4 into mu o minus mu e is the equation for thickness of the quarter wave plate in the case of negative crystal like calcite. For a positive crystal like quartz, velocity of the ordinary ray is greater than the velocity of extraordinary ray. Hence, mu e is greater than mu o, because for mu e, for positive crystal, mu e is equal to C by VE minimum. Here, velocity of the extraordinary ray for positive crystal is minimum perpendicular to the direction of the optic axis. As VE is minimum, mu e is large. So, mu e is greater than mu o for positive crystal. Hence, if d is the thickness of the crystal plate, the part difference between the two components delta is given by d into mu e minus mu o, because mu e is greater than mu o for the positive crystal. And also we know that the quarter wave plate produces a part difference of delta is equal to lambda by 4. Then equate these two equations, we get d into mu e minus mu o is equal to lambda by 4, or d is equal to lambda by 4 into mu e minus mu o. In general, for any quarter wave plate, the thickness of the quarter wave plate is given by d is equal to lambda by 4 into mu e difference mu o. So this difference may be positive or negative depending upon, mu e and mu o are replaced depending upon the positive or negative crystal. What is the importance of the quarter wave plate? A quarter wave plate is used for the production and detection of circularly polarized light. This is very important. A quarter wave plate is used for the production and detection of circularly polarized light. In conjunction with a nickel prism, it is used for analyzing any kind of light. What is a off-wave plate? In this plate is also made from a doubly refracting uniaxial crystal of calcite or quartz with its refracting surfaces cut parallel to the optic axis. The thickness d of the plate is such that it introduces a phase difference of pi or a part difference of lambda by 4 between the ordinary ray and the extraordinary ray in passing through it when light is incident normally on the face of the crystal, not face of the crystal. The plate cut such that it is made up of doubly refracting uniaxial crystal of calcite or quartz with its refracting faces cut parallel to the optic axis, and the thickness of the plate is such that it can introduce us a phase difference of pi or a part difference of lambda by 2 between the ordinary ray and the extraordinary ray in passing through it when light is incident normally on the face of the crystal. This is very important. In the case of quarter wave plate, there is a part difference of lambda by 4, but in the case of off-wave plate, there is a part difference of lambda by 2. Off means of the wavelength. That is why it called off-wave plate, because it introduces a part difference of the wavelength between the ordinary ray and extraordinary ray. That is why it is called off-wave plate. The thickness of the off-wave plate can be obtained similar to quarter wave plate. If d is the thickness of the crystal plate, then the part difference between two components on coming out is delta is equal to d into mu e minus difference mu o. The off-wave plate produces a part difference of delta is equal to lambda by 2. We have d into mu e difference mu o is equal to lambda by 2, or the thickness of the Offwave plate is given by d is equal to lambda by 2 into mu e difference mu o. So this difference may be negative sign, and also we can interchange mu e and mu o depending upon the type of the crystal, whether it may be positive crystal or negative crystal. This difference sign becomes minus, and also mu e and mu o you can interchange. In general, the thickness of the Offwave plate is given by d is equal to lambda by 2 into mu e difference mu o. So these are the books I have used for the reference to make this video. Thank you for watching.